And my name is Henry Alfasiregar. We are from Indonesia. We studied computer science in State University of Malang. And now we will presentation about mathematical induction. Do you know what is mathematical induction? What is the example and how it works? So let's learn together.
Mathematical induction. Mathematical induction is a special way of proving things. It has only two steps. Step 1. So it is true for the first one. Step 2. Show that if any one is true, then the next one is true. Then all are true. Have you heard of the domino effect? Step 1. The first domino falls. Step 2. When any domino falls, the next domino falls. So, all dominoes will fall. In the world of number, we say Step 1. So, it is true for n equal 1. Step 2. Show that if n equal k is true, then n equal k plus 1 is also true. How to do it? Step 1 is usually easy. We just have to prove it is true for n equal 1. Step 2 is the best done this way. First, assume it is true for n equal k. And the second, prove it is true for n equal k plus 1. Don't forget, we can use the n equal k case as a fake. Step 2 can often be tricky because we may need to use imaginative trick to make it work. Like this example. Okay, the example is 3 to the power of n minus 1 is a multiple of 2. Is that true? Let us find out. First, show it is true for n equal 1. 3 to the power of 1 minus 1 equal 3 minus 1 equal 2. Yes, 2 is a multiple of 2. That was easy. So, 3 to the power of 1 minus 1 is true. Okay, the next step is assume it is true for n equal k. 3 to the power of k minus 1 is true. Hang on, how do we know that? We don't. It is an assumption that we treat as a fact for the rest of this example. Now, prove that 3 to the power of k plus 1 minus 1 is a multiple of 2. 3 to the power of k plus 1 is also 3 multiple of 3 to the power of k. And then split 3 into 2 and 1. So, each of these are multiple of 2. Do you know why? Okay, the reason is because 2 multiple of 3 to the power of k is a multiple of 2. We can say that because we are multiplying by 2. Okay, the second reason is because 3 to the power of k minus 1 is true. We already said that in the assumption above. So, 3 to the power of k plus 1 minus 1 is true. So we are done. Really simple, right? And very, very easy. Did you see how we use the 3 to the power of k minus 1 case as being true? Even though we have not proved it, that is okay, because we are relying on the domino effect. We are asking if any domino fall, will the next one fall? So we take it as a fact, or we can say that is temporarily that the unequal k domino fall, and see if that means the n equal k plus 1 domino will also fall.
Tricks. I said before that we often need to use imaginative tricks. A common trick is to rewrite the n equals to k plus 1 case into two parts. One part being the n equals to k case, which is assumed to be true. The other part can then be checked to see if it is also true. We did that in the example above, and here is another one. Example, adding up odd numbers. 1 plus 3 plus 5 plus blah 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 plus 2n minus 1 equals to n square. First, so it is true for n equals to 1. 1 equals to 1 square is true. Second, assume it is true for n equals to k. 1 plus 3 plus 5 plus blah 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 plus 2k minus 1 equals to k square is true. Now, prove it is true for k plus 1. 1 plus 3 plus 5 plus blah 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 plus 2k minus 1 plus 2 times k plus 1 minus 1 equals to k plus 1 square. We know that 1 plus 3 plus 5 plus blah 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 plus 2k minus 1 equals to k square, the assumption above. So, we can do a replacement for all but the last term. K square plus 2k plus 1 minus 1 equals to k plus 1 square. Now, expand all terms. K square plus 2k plus 2 minus 1 equals to k square plus 2k plus 1. And we can simplify k square plus 2k plus 1 equals to k square plus 2k plus 1. They are the same, so it is true. So the conclusion is 1 plus 3 plus 5 plus blah 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 plus 2 times k plus 1 minus 1 equals to k plus 1 square is true. Done it!
So, the conclusion of mathematical induction is a method of mathematical proof typically used to establish a given statement for all natural numbers. It is a form of direct proof, and it is done in two steps. The first step, known as the base case, is to prove the given statement for the first natural number. The second step, known as the inductive step, is to prove that the given statement for any one natural number implies the given statement for the next natural number. From these two steps, mathematical induction is the rule from which we infer that the given statement is established for all natural numbers. Now, we will tell you the history about mathematical induction. In 370 BC, Plato's Parmenides may have contained an early example of an implicit inductive proof. The earliest implicit traces of mathematical induction can be found in Euclid's proof that the number of primes is infinite and in Besar's cyclic method. An opposite iterated technique, counting down rather than up, is found in the Zorid's paradox, where one argued that if 1,000,000 grains of sand form of heap, and removing one grain from a heap left it a heap, then a single grain of sand, or even no grains, form a heap. An implicit proof by mathematical induction for arithmetic sequence was introduced in the Al-Fahri written by Al-Karaji around 1000 AD, who used it to prove the binomial theorem and properties of Pascal's triangle. None of these ancient mathematicians, however, explicitly state the inductive hypothesis. Another similar case, or contrary to what Vaca has written, as Prudental carefully showed, was that of Francesco Maurolico in his Arithmeticorum Libri Duo, who used the technique to prove that the sum of the first and odd integer is n squared. The first explicit formulation of the principle of induction was given by Pascal in his Traité du triangle arithmétique. Another Frenchman, Fermat, made ample use of a related principle, indirect proof by infinite descent. The inductive hypothesis was also employed by the Swiss Jacob Bernoulli, and from then on it became more or less well known. The modern, rigorous, and systematic treatment of the principle came only in the 19th century with George Boole, Auguste de Morgan, Charles Sanders Peirce, and Giuseppe Peano.
Thank you for watching our video. Bye-bye.